Hello everyone. So today in this video we will give some examples regarding the confidence interval and the hypothesis testing of for the difference of two means. So our first example is about comparing the fuel consumption, the gas mileage. So a study was conducted in which two types of engines, engine type A and B, were compared. So the gas mileage or the fuel consumption, okay, let me just write the fuel consumption of two engines are compared, okay. So the first engine, you have an experiment, you have 50 experiments regarding engine type A, and you have 60 experiments regarding engine type B. So the variables are XA is the gas mileage using engine type A, and XP is that of the gas mileage of engine type B. So it turns out that the same type of gasoline and road and weather conditions apply in all of the experiments. And the data summarized as follows. So it turns out that for 50 many cars, so remember I have N1 that's equal to 50, okay, and N2 that was equal to 60. So N1 is equal to, for 50 many cars, the average consumption is, it's not the consumption, but, so the average kilometers per 1 liter is given as 14.4. So as you might as you might see, this is a little bit different than the measures, than the unit that we use in Turkey. So in Turkey, what we use is how many, let's say, liters, how many liters, okay, per 100 kilometers. So this is the average, this is the unit or the key performance indicator that we use for cars. So for example, if the car has a low consumption, then for example I'm just telling, for example, 5 liters, okay, per 100 kilometer, that's a good car, okay, that's a car which has let's say low consumption. But this unit is just vice versa, it's not liter per kilometer, but it's kilometer per liter. So engine type A, it's able to make on the average 14.4 kilometers per 1 liter. And engine type B, it just travels on the average. So this is the average of 60 many cars. Okay, don't forget this. So their average is 12.2 kilometers per 1 liter. Okay, so which one is better? Well, it seems the first one is better because using 1 liter, it's able to make, let's say, XA bar x bar A or x bar B, that's equal to 12.2 kilometers. Okay, so it turns out that, well, A seems better. Well, the population standard deviations are known as 5 kilometers per liter for A, okay, and 4 kilometers per liter for B. So the first question is test whether mu1, or let's say this is not mu1, but let's say this is mu A, okay, is equal to mu B or not, with alpha equal to 0.04 significance level. And let's find the 90% confidence interval for mu A minus mu B, okay? So this is the question. Well, let me ask you something. So it turns out that, well, the average of A is greater than average of B. Okay, so this is not 12.2, but this is what? 2.2 kilometers per liter. So why do we need a test like this, which says mu A is equal to mu B or not? So why do we have a test like this? Okay, so um, let me just change this so that don't get confused here. Okay, that's great. Okay, so why do we need this test? Why do we need this test? Because, so I'm asking this because we already see that x bar A minus x bar B, that's equal to 2.2 kilometers, right? Why do we need to test this one? That's because, well, this is the average of a sample of 50 many cars, and this is the average of a sample of 60 many cars. Okay, so these are the averages of samples. The question is not regarding the samples. The question is regarding the parameters themselves. What does this mean? Well, we want to test whether the cars, all of the cars that are produced and will be produced using engine type A, their full consumption, and here this is the full consumption of all of the cars that are produced and will be produced using engine type B. I'm just trying to see whether these parameters are equal or not. These are these are sample averages, but these are the population averages or population means, okay? So what I'm trying to do is just by looking at the sample means, I'm trying to decide, okay? Just look at this and decide on the population mean, okay? So this is what I do. In fact, this is what I do in all of the statistics course, okay? So let's try to make this test. Well, the hypotheses are, well, whether A is equal to B or mu A minus mu B is equal to 0 or not. Okay, so this is my hypothesis. So what is the test statistic? Remember, the test statistic is Z, that's equal to x1 bar minus x2 bar. So I have here xa bar minus xb bar minus mu A minus mu B, right? So because xa bar minus xb bar, it was a normal random variable with this mean. And what was the standard deviation? Standard deviation is sigma 1 square divided by n1, sigma 2 square divided by n2, okay? And what is mu A minus mu B? It comes from the hypothesis, which is 0, okay? So this is my Z. Well, what is step 3? Just find the critical region. So this is Z sub alpha over 2. Alpha was 0.04, so this is 0.02. Well, this is my rejection region. Real numbers minus 2.05, 2.05. Okay, so if you just check it on the plot, it's something like this. So you have 2.05 here, and you have minus 2.05 here. So these are the rejection region, okay? This part is the rejection region, and this part is the rejection region. So what is Z observed? So just using this formula, just calculate the Z observed, which is 14.4 minus 12.2 minus 0. 0 comes from the hypothesis. This is x bar A. This is x bar B, okay? Divided by sigma 1 square divided by n1, sigma 2 square divided by n2. And well, the result is equal to 2.51. See? So 2.51, just check. 2.51 is in this region, right? It's greater than 2.05. Hence, what we do, we just reject the hypothesis. What does it mean, reject the hypothesis? It turns out that, well, the gas mileage or the fuel consumption of a engine type A is not equal to engine type B. Okay, so we just reject this hypothesis, right? Okay, now just find the confidence interval. So remember the confidence interval, its formula was xa bar minus xp bar plus minus the alpha over 2 times sigma a square na sigma b square nb, right? Just plug in the values. It turns out that, well, mu a minus mu b, the difference is between 0.41 and 3.99, okay? So at what level, of course? So this is a 96% confidence interval, okay? So I am 96% sure that the difference of A and B is between 0.40, let's say almost, and 4, okay? So what does this mean? What does this mean? Well, this mean by 90%, I am sure that there is a positive difference between mu A and mu B. Okay, so I am 90% sure that there is a positive difference between mu A and mu B. And moreover, I am 96% sure that, well, the difference between A and B is at least 0.41, okay? So I can say that I am 96% sure that mu A is greater than mu b plus 0.41. So the engine type A is at least 0.41 kilometers. So it's able to travel at least 0.41 kilometers per liter when you just compare with mu b. Okay. And remember, we just say that for the same level of alpha, confidence interval is equivalent to hypothesis testing, okay? So just recall the previous question. We just solved whether mu A minus mu B is equal to 0 or not, okay? So if we just solve this question and look at this confidence interval, then since 0 is not in the confidence interval, we can say that, well, I reject the hypothesis. Why? Because 0 is not in the confidence interval. Remember, it should be just both of confidence interval and hypothesis testing should use the same alpha, okay, with alpha equal to 0.04. So for example, if I just ask you, just test whether mu A minus mu B equal to 0.40, okay, versus it's not equal to 40. What's your answer? Well, just look at here again. Is it in the interval, in the confidence interval? No, it's not in the confidence interval. Hence, you just reject this hypothesis again at what? At alpha equal to 0.04 significance level. Okay, great. Now, another example is comparing the chemical concentration in a river. Okay. So a study was conducted to estimate the difference of the amounts of the chemical orthophosphorus measured at two different stations on a river. So this is a chemical thing, okay, orthophosphorus. So what they do is they have two different stations in a river, and they just measure the amount of this, the amount of orthophosphorus in milligrams per liter. So there are 15 samples from station 1 and 12 samples from station 2. And X1 is the amount of chemicals measured at station 1, and X2 is the amount of chemical measured at station 2. Um, so, well, it turns out that the data summarize as follows. So this is 2. Okay, sorry for this. This is 2. Well, X1 bar, that's equal to 3.84 milligrams per liter, and the standard deviation of the first observation is 1.65 with 15 many observations here. And there are 12 observations with 0.92 milligrams per liter as the standard deviation and 1.49 milligrams per liter, okay, as the average of 12 observations. Well, assume that the variances are unknown. We don't know the variances, but you can assume that they are equal to each other. Well, find a 95% confidence interval for the difference between the true mean content at these two stations. That is, find a confidence interval on mu1 minus mu2. Okay? Well, remember, since we assume the variances are equal to each other, then we can use the pooled estimates. Remember the pooled estimate, okay, which is given by this formula. And one minus one dot 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 and so on and so forth. If you just plug in the values, the pooled estimate is equal to 1.897. Okay. And from t-table, we have 95 degrees of, so sorry, we have 95 degrees of freedom. Why? It comes from this formula. Remember, this is n1 plus n2 minus 2, which is 12 plus 15 minus 2. That's equal to 25 degrees of freedom. Remember, this was the good formula. Okay, this was the good formula. So I can memorize this. I can just calculate this easily. So the t value with 25 degrees of freedom, if you just look at the table, it turns out that it is 2.06. Okay. So 95% confidence interval is given by x1 minus x2 bar plus minus t alpha over 2 times sp times 1 over n1 plus 1 over n2. Okay. If you just plug in the values, the differences between the confidence interval is between 1.25 and 3.45. Okay. So again, if I just ask you at alpha equal to 0.05 level, right? Sorry, yes, alpha equal to 0.05 level. How about testing whether the concentration is equal to each other or not? Okay. Well, what is the answer? Well, since this means mu1 minus mu2 is equal to 0, and 0 is not in this interval, okay? Not in, it's not in this interval, right? In this interval, right? Hence, we just reject this hypothesis, okay? Or if I just ask you whether the difference is equal to 1, okay, so let me just say mu1 minus mu2, that's equal to 1. Again, you will just reject this because it's not in the confidence interval. So I am 95% confident that mu1, okay, mu1 is at least 1.25 grams per liter greater than mu2. Okay, so the station at the first station has in liters 1.25 gram more orthophosphorus than the second station. Now the same question, but now what we do is, well, so in the first one, we just assumed that the population variances were equal, okay? But, well, I'm not comfortable with the assumption that they are equal to each other. So let's drop this assumption, okay? Don't assume that they have equal variances. And by just using the formulas that we see for unequal variances, construct another confidence interval again, right? So remember, when sigma 1 is not equal to sigma 2 squared, right? Then we have that messy formula. Oh, I didn't write it here. So it was the formula for like this. It was something like, I don't know, but S1 squared divided by N1 squared plus S2 squared divided by n2 squared, it just goes like this. So I just calculated it for you. It turns out that that's equal to 22.6, which is, you can just take it as 23. So if you just look at the value of t random variable at 23 degrees of freedom, 0.0 t sub 0.025, it turns out that its value is 2.07. So it's very equal to 2.06, which was in the previous question with b is equal to, remember how many degrees of freedom? 25 degrees of freedom, right? It's very, very similar to that value. And the confidence interval is given by now 1.31, okay, times and 2.39. So remember the difference. This is the same. Plus minus t alpha over 2. This is the same, but now I have b equal to 23 degrees of freedom. The degrees of freedom has changed. So in the previous formula, I have, remember, sp times what? 1 over n1 plus 1 over n2, okay? So this is the difference because we just assume different variances. Hence, we just use different estimators for different variances. Okay. So in the next video, we will talk about the paired observations and we will see some plots regarding how to compare the means by just looking at some different plots.